Okay, this video is a pretty important one. It is called the Fundamental Theorem of Calculus. So there's actually two parts to this. I'm going to briefly discuss the first part, do a couple of examples, and then towards the end of the video come back and really get into what this means. So here's the basic idea. You have a function that's part of an integral. And then we're going to call g the function that is that integral. So g of x is the integral from a to x, so that's my variable here, of f of t dt, where a is a constant, and it is the start of our interval from a to b that x value will exist in. Okay, so we're trying to find the area under the curve from a to some x value, the curve is f, and anyway, we're calling that function g. The idea is, this is the important part here, if I were to take the derivative of g, okay, so this is my function g, if I were to take the derivative of g, I simply just get f, whatever this function is right here, evaluated at x. Okay, so a quick example of that. Find the derivative of the function g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. G prime of x will simply be this function, the square root of 1 plus t squared, evaluated at x, which means 1 plus x squared. And that is it. That is the derivative of g. It could get slightly more involved here. Notice on the second example, this isn't just x up here, it's x to the fourth. So there's an additional step we're going to have to take here, but I still want to find the derivative of this. So the derivative of the integral from 1 to x to the fourth of the secant of t dt is equal to that function, the secant, evaluated at whatever this is up here, x to the fourth. Okay, so in this example that was just x. The secant of x to the fourth. However, if this is not just x up here, what you would have to do at this point in time is chain on the derivative of whatever that value is at the top of your integral. So the derivative of x to the fourth. So that's the only thing that you have to worry about that might be a little bit different there. Is this thing at the top of my integral not just x? And if that's the case, I need to chain on the derivative of that thing when I'm done. And that's it. Okay. The second part of the fundamental theorem of calculus. This is the single most important thing that we are going to do moving forward in calculus. And that is if we have a continuous function and we do the integral of it, the integral of f of x dx from a to b, it is simply equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. Okay, so that means that the derivative of f of capital F is equal to f. So what we are going to do is simply take the antiderivative of f and then evaluate at the endpoints of my integral, and that will give me the exact solution of this integral. Okay, which again, when we do that, we're finding area under a curve of a graph. So find the area under the curve y equals x squared from 0 to 1. So the integral that we would set up here is we would do the integral from 0 to 1 of our function x squared dx. To evaluate this, we are to take the antiderivative of our function, which would be 1/3 x cubed. Now, when you just practice antiderivatives, you always put plus c, right? We could say there could be a constant. Now, it does say that f is any antiderivative of f, which means that c could be anything that we want it to be, and the easiest thing to make c be is 0, right? So if I just say, well, c is 0, then I don't have to worry about putting a plus c here. I'm going to go ahead and put plus c just to show you why we don't need to put plus c. Okay, so I'm going to do this, and I'm going to evaluate it, and you'll see why it's not really necessary to put plus c. Because, again, c could be any constant that you want it to be. And I just want to show you that no matter what you put there as that constant, it really doesn't matter. And so you might as well make c be 0. Okay, so this is going to be something that you don't actually need to do moving forward, but I'm going to show you that here. So I'm going to do the antiderivative, which is 1/3 x cubed plus c, and then I'm going to evaluate that from 0 to 1. So the way I'm going to show that is I'm going to put a bracket here, and I'm going to say from 0 to 1. And then if you look at what we're going to do next, it's going to be evaluate that antiderivative at b and then a. So I'm going to evaluate it by plugging in 1, and then evaluate by plugging in 0, and I'm going to subtract those two answers. So what this is going to give me is 1/3 of 1 cubed plus c minus 1/3 of 0 cubed plus c. And if you evaluate this, 1/3 of 1 cubed, that's 1/3, plus c. This would be 0, so minus 0. And then if I distribute that negative, that's also minus c. So what happens? Well, regardless of what I put for my constant, I'm always going to have this happening, plus c minus c. I don't need to put that. Okay, so this right here, completely unnecessary whenever you do the antiderivative. You don't need to put plus c. That is if it is a definite integral, okay, which means we have these bounds. And I'm evaluating it. I don't need to put that plus c. So what do I end up with? I end up with an answer of 1/3. So that tells me that the area under the curve of x squared from 0 to 1 is exactly 1/3. Okay, so evaluating definite integrals. I'm going to go through a couple more examples here a little bit more quickly. So again, the idea is you take the antiderivative of the function, which the antiderivative of e to the x is simply just e to the x. We're going to evaluate from 1 to 3, which means I'm going to do e to the third minus e to the first. Look, that's a precise answer, e to the third minus e to the first. I could evaluate those. What if I did, I would get something like 17.37. It's an approximation of that. The actual preferred answer here is the exact one when dealing with things that aren't going to give you exact answers. So dealing with decimals, I would say leave it as e to the third minus e. That's more precise than 17.37. But if you want to know about what that value is, go ahead and evaluate those. Okay, same thing with number 2 here. So I'm going to do the antiderivative of 1 over x, and the antiderivative of 1 over x is the natural log of x, and I'm going to evaluate that from 3 to 6, which means I'm going to do the natural log of 6 minus the natural log of 3. Now again, that is a precise answer. If I evaluate the natural log of 6 and I subtract the natural log of 3, I get 0.693. It's an approximation there. Okay. Next example. Find the area under the cosine curve from 0 to b, and then evaluate when b is pi over 2. So, integral. I'm supposed to evaluate this from 0 to b. Our function is simply just the cosine of x, and then I'm gonna put in the dx. That's telling me that my variable of integration is x. We are going to take the antiderivative of cosine. So the antiderivative of cosine is sine. The sine of x. We are going to evaluate that from 0 to b, which means we get the sine of b minus the sine of 0. Well, the sine of 0 is 0, so that means that my final answer here would be the sine of b, but then it tells me to go ahead and evaluate when b is pi over 2. So if b is pi over 2, that means I would simply just get the sine of pi over 2, which is 1. Okay, so the main idea here in the fundamental theorem of calculus is that differentiation and integration are inverse processes. So just like addition and subtraction, or squaring and square rooting, those processes are inverses. They undo each other. Taking a derivative, evaluating an integral, those two operations are inverses. And so let me go back, now that we know more about how to evaluate the second part of the fundamental theorem of calculus, now that we know how to evaluate a definite integral, let me go back to this first theorem here, this first part of the theorem, and describe why hopefully this makes sense. So if I were to evaluate this, so that would be evaluating g, right? If I were to evaluate that integral, what that would tell me is this, right? I would have the antiderivative of f, which I'm going to say capital F. I would have that evaluated at x minus that evaluated at a, whatever that constant a would be. That would be my solution to that. Okay. Well, if I were to find g prime, so that's g, right? That g would be my antiderivative, solve those things. If I were to do g prime, that would be take the derivative of that. Well, if I were to take the derivative of this, what I'm doing is I'm doing the derivative of the antiderivative, right? So the derivative of the antiderivative evaluated at x would simply just be little f of x. And then I would be doing the derivative of the antiderivative evaluated at a. Now, a is a constant. So if I evaluate the antiderivative at a constant, that is going to be a constant. I'm going to get a value from that. And if I take the derivative of that constant, that's going to be 0, which means it goes away. So I simply end up with f of x, which is exactly what that first part of that theorem tells us. Okay, so that's the first part of the theorem. The second part of the theorem is actually how do you evaluate a definite integral, and that is to do the antiderivative and then evaluate at your endpoints and subtract those values.